Here you see a universal asynchronous receiver-transmitter integrated circuit. The UART is a special digital IC which contains separate data transmitter and receiver sections. The transmitter section of this IC will accept parallel data from the MPU, then transfer the data in serial form to the peripheral device. The receiver section, on the other hand, will accept the input data in serial form, then convert it to parallel data for processing by the microprocessing unit. Basically, the UART makes the task of receiving and transmitting data in serial form easier for the processor. Most universal asynchronous receiver-transmitter ICs are capable of being programmed by the end user to determine the word length, baud rate, parity type, even or odd, parity inhibit, and the stop bit length. The UART also provides 6 status flags. These are transmission complete, buffer register transfer complete, received data, parity error, framing error, and overrun error. We will briefly examine the function of each pin on this IC. Pin 1 is labeled VCC. It will connect to the positive 5-volt side of the DC power source. Pin 2 is labeled VEE. It is commonly connected to the negative 12-volt power supply. Pin 3 is labeled GND. It, of course, is connected to the ground plane. Pin 4 is labeled RRD. It is the receiver register disconnect input. A high on this pin places the receiver data output pins, which connect to the MPU bus line, in a high impedance state. A low input, on the other hand, allows the receiver data output pins to connect to the data bus. Pins 5 through 12, which are labeled RB1 to RB8, are the receiver data output lines. The data received from the serial input pin is converted to parallel form, then transferred through pins 5 through 12 to the microprocessor. Pin 5 is the least significant bit, and pin 12 is the most significant bit. Pin 13, which is labeled PE, is used to indicate a parity error. A high on this pin indicates that the parity of the received data does not match the parity programmed at pin 39. Pin 14 is labeled FE for framing error. A high at this output indicates that no valid stop bits were received. Pin 15 is labeled OE for overrun error. A high on this pin indicates an overrun condition. This condition may occur when the data received input is not reset before the next character was received by the internal receiver holding register. Pin 16 is labeled SFD for status flag disconnect. When pin 16 is brought high, it places pins 13, 14, 15, 19, and 22 in a high impedance state. This allows the status flags from several universal asynchronous receiver transmitters to be connected to the same communication bus. Pin 17 is labeled RRC. This is the receiver clock input pin. The clocking frequency on this pin should be 16 times the desired baud rate. Pin 18 is labeled DRR. It is the data receive reset. When this pin is brought low, it resets the data received flag. Pin 19 is labeled DR. It is the data received flag input. A high on this pin indicates that the data was received and is in the receiver holding register. Pin 20 is labeled RI. It is the receiver serial input. All serial input data is applied at this input. Pin 20 is held high when no data is being received. Pin 21 is labeled MR and is the master reset. A short pulse applied to this pin will reset the registers and flags in both the receiver and transmitter sections. Pins 22, 24, and 25 will be set high, while all other registers and flags will be set low. Pin 22 is labeled THRE. This is the transmitter holding register empty pin. A high on this pin indicates that the data in the transmitter input buffer has been transferred to the transmitter register. This allows new data to be loaded. Pin 23 is labeled THRL. It is the transmitter holding register load pin. A low on this input allows the data being applied at inputs TB1 through TB8 to be entered into the transmitter holding register. A high on this pin then transfers the contents of the transmitter holding register to the transmit register. Pin 24 is labeled TRE. It is the transmit register empty pin. This pin will remain high until a transmission of data takes place, at which point pin TRE drops low. Pin 25 is labeled TRO. It is the transmitter output for the serial data. All data and control bits are output on this pin. The TRO remains high when no transmission is taking place. Pins 26, 27, 28, 29, 30, 31, 32, and 33 are the data inputs from the microprocessor. Pin 26 is the least significant bit, and pin 33 is the most significant bit of the input data. These pins are labeled TB1 through TB8. Pin 34 is the control register load pin and is labeled CRL. This pin is generally wired permanently high. However, it can also be strobed with a short positive going pulse if it is desired to change certain parameters of the IC. When this pin is high, the programmed instructions on pins 35, 36, 37, 38, and 39 are loaded into the internal control register. Pin 35 is labeled PI. It is the parity inhibit pin. A high on this pin will disable the parity generation and verification function of the IC and force pin 13 to a logic low condition. Pin 36 is labeled SBS. It is the stop bit select pin. The UART can be programmed for the number of stop bits to be added to the data word output. A high on this pin will cause the IC to generate 2 stop bits if the data word length is 6, 7, or 8 bits long. A low on this pin will cause the IC to generate only 1 stop bit. Pins 37 and 38 are the word length select pins. They are labeled WLS1 and WLS2. These pins are used to select the data bit length. Pin 39 is the even parity enable pin and is labeled EPE. When this pin is high, the IC checks for even parity, and when the pin is low, the IC checks for odd parity. Pin 40 is labeled TRC. It is the transmit clock input pin. The clocking frequency on this pin should be 16 times the desired baud rate. Generally, the transmitter and receiver sections are operated at the same baud rate. Therefore, you will normally find both clock pins, TRC and RRC, wired together and fed by a common clock circuit. As you can see, the universal asynchronous receiver-transmitter integrated circuit communicates in parallel with the CPU and outputs or inputs data in serial form to the connected peripheral device. This classifies the UART as a serial I/O device, since the data is handled in serial form to and from the peripheral device. Here you see the typical data format for a UART device. Since the serial input or serial output is held at a high impedance state, they must be brought low to start the transmitting or receiving of data. Therefore, the first bit in the transmitted data will always be a low bit. The low start bit is then followed by the data contained in the data bit group. The next bit following the data information is the parity bit. If this bit is high, then even parity is used. If this bit is low, odd parity is used. The following 1 or 2 bits are the stop bit codes. The stop bits are used to tell the processor that the data is completed. The start bit, parity bit, and stop bits are used to replace the separate control lines which would be required in the typical parallel I/O configuration. Once the start bit swings low, the UART alerts the processor that the peripheral device has data to transfer. The processor then acknowledges the signal from the UART and allows the data to be transferred from the UART IC to the CPU. After the stop bits have been received, the processor continues with other operations. We will now pause for a short review of the most recently discussed material. Parallel communications are a much faster form of data communication. This is due to the fact data is transferred in parallel. However, when data must be transferred over long distances, serial communication methods are preferred. The Universal Asynchronous Receiver Transmitter IC is a common serial I/O device. It is capable of receiving and transmitting data information in serial form to connecting peripheral devices. The serial information received is converted into parallel information before it is directed to the processor. In the same respect, the processor sends parallel data to the I/O device, where it is converted into a serial format before it is transmitted to the peripheral device. The serial formatted data must contain certain control bits. These are the start bit, parity bit, and the stop bits. Other control bits may also be included. This concludes review number 4. Next, we will examine the video input-output system.